So now that we understand how optimization in Torch works, let's consider an actual generative model. And the easiest example of generative models is to generate random names. So a name like, let's say, Anna or William, Thomas is a sequence of characters, and there's a certain likelihood that an H would follow a T and that an O would follow an H. And you can see that this is a little confusing because there's a certain likelihood that an A is followed by another N, by an N, but here an A is followed by an M, and here an A is followed by an S. So in this case, we would say, if we only had these three names to learn from, we would say an A can be followed by an N, by a space, this is the terminating character in this case, by an M, or by an S, and so we would say these probabilities are 1/4 and the other probabilities are 0. Now if I throw in another name like my own, Nicholas, then this already changes because we already have to take the character U into account. So how can we create a model like this? And by the way, this is called a bigram model because you are using two characters, so that's the word bi. Is to go to a name database. Like this is something that is public. This is from the SSA, the Social Security Agency, and these are all the baby names in the US. So these are quite a large number, and we can, to stick with our example, we can look at the likelihood of the bigram AN, and we find 17,000 here in this list. We can look at the likelihood for AS, and we would find 3,896, and so on. So we can do this using a computer and compute the likelihoods of all possible bigrams. And if you think about this real quick, is you have 26 characters in your alphabet, you have a space character, so it's 27, and everything can be followed by everything, so we have a matrix of 27 by 27 characters. So let's do the following. Let's get this data, and we can use the exclamation mark to trigger shell commands, and this will actually allow us to download the data to our hard disk. So we can open this up, and it's called all names text, and wow, this is already doing a lot of things that we want to do. I want to read it line by line, yes, but then I actually want to split it into lines, so this looks like that. Now, what did we get? Let's see, it's a long list. Does that has a shape? It's not a PyTorch array. Yeah, that only works for PyTorch tensors, but we can get the length of it like this. So we have 100,364 names in our list. Let's look at them again, and as you will see, it uses capital letters as well. This makes it a little more complicated because then we have to take all the capital letters into account as well. So what we should do is we should lower them all, and one way of doing this is we go through the list, we take individual names and lower them for all the name in names. And if you do that, you have a lowered list. Now, the next thing to feed this into any machine learning model will require to do something that is called tokenization. And so what we do is we take text, images, sound, or whatever, and turn that into numbers. And of course, the easiest way to do this here is we would say, well, A is the first character of the alphabet, Z is the 26th. And let's do that real quick. We should extract all the characters that are in here, and I could write down A, B, C, D, but then who knows, maybe there's a character that is not used in, no, just kidding. But technically, the easier way to do this, or the correct way to do this, is we would take all the names and join them into one big string. It looks like this. And then we turn it into a set, which will drop all of the characters that are in there twice. Now we have a set of all the characters that are in the list, and surprise, surprise, it's really all of the 26. Now we want to turn it into a list and maybe make sure these are sorted. I think they already are, which is an artifact. And now we want to add the space character in front of it, like so, so that we have a list of 26 characters plus the space. Now we can call this our alphabet, and this is basically all the tokens that we can have. Well, wants to do it this way. It's weird. Remove this. Now in order to tokenize it, we need to take every character and turn it into an integer, and the other way around. And so the way to do this is we can enumerate the alphabet to get all of the indexes and the characters. So this looks like so. We get the indices and the characters in this, and we can print this out. So we have something like this, and now we can create two dictionaries, one that allows us to map all the indices to a character, and another that does map all the characters to the index. So we call this the index to character. So given a character I, actually it already does this because this is such a typical thing to do. Just need to add the curly brace here. So it goes to those and it says, okay, this is the index, the key of the dictionary, and it returns the character. Here I index it with the character and it returns the actual index value. All right, so what do we have? We have all the names. You've seen them. We know how many there are, and we can now go on and think about how to process our data. So the model we chose is a bigram model, which would be 27 by 27 values, which would be the probability that one follows the other. And we can do this in Torch using a tensor. But before we do this, let's just make sure we are starting from a clean slate here, and we use random values using, and we want to have 27 by 27 values, and then we require grad because we want to later learn these values and optimize a loss function to get the W matrix that represents our data set. So the naive way, or actually the simple way and the best way to do that here, would be to actually count everything. And I can do the following. I can actually ask Gemini to do that for us, and I've asked this already before, and it does work. Can you please compute the probability of all bigrams in the list names containing names or strings and storing them in 27 by 27 tensor, which has been initialized. I just explain how the data structures look like. So it's now running the algorithm it came up with, and this is pretty straightforward. It is actually taking all of the names. It adds a space in front and a space at the end, so we get the bigram for the start character and the bigrams for the last character. And here what it does is it takes the names, and then it takes the names shifted by 1, which is basically the character that follows the other name. So if the name would be Anna, then this whole thing shifted by 1 would be N and A, space. Then it actually gets the first and the second character and creates a big matrix N, which is keeping track of the number of bigrams. And then it essentially normalizes it and stores it into a tensor W. And this is what I asked it to do. And the tensor W doesn't exist here. It's because here I have the, I only define it down there. So for this really to work, we would need to copy this up. All right, so I want to keep this because if our learning works, it should actually get the exact same result because this is the optimal outcome. It actually takes quite some time, as you can see, because it's a big deal to go through the 100,000 characters, names, character by character, and counting this. So how does it look like? Like this. These are logits, and we will talk about this later. Here you see it actually exponents them, and this will make sure that there are no values that are negative. So let's keep this value here, and we call this W counted logits is like W. So just for the record. So before we train this, let's think about how we can actually use this data. If we want to generate random names using this matrix W, which contains probabilities after exponentiating, I could think about the following. Well, each row consists through a bigram. So this would be, the first row would be AA, then the first row would be on A, and so this would be AA, AB, AC, AD, the probability that these bigrams exist. If we have something like this, what we could do is we could actually sample from these probabilities and say, let's say we are given the character A, we can generate a random bigram by sampling from all of these probabilities as a multinomial distribution. So let's do this real quick and write code which we will call generate name. And for this we want to generate a random name that initially starts as an empty list, and we want to pick a random character that is a random character out of the alphabet that we have. And so this could be even the space, and in this case we would be over immediately, but most likely it would be some other character, and then it would go on to draw them until we would draw another space. So we can now append this to our random name, and for this we have to take the random character, which is an integer, and turn it into a character. So now we have a random name. So and now at the end we want to return random name, and we can already test this by just calling it, and let's see what happens. It should generation. Now this is only generating a single character. So what's next? We want to go and add more of these and say, while the random character is not 0, we will add 1. So I can already copy and paste this down here. This is how it's going to end. What we would want is we want to have a list of probabilities and say random character, and the probability is P, call from multinomial. So you see, this is not always helpful. This is not what I want to do. And take a list of probabilities and then give me one of them, and then turn this into an item. Now what is prop? Prop should be the row of the matrix W after exponenting it. And now we could say, let's say we want to get, we start with the letter, what was this, P, and in this case this would be C to I of P, and now we want to get the entire row, So it would be grabbing one of those rows. And now I can draw from this probabilities what the next character would be. And let's see what the random name would be. And by the way, we should always do this torch manual seed 42, so this keeps being the same. And in this case, we get, well, we will get a very long name here because it only at the very end stops being, and so maybe we can write that like this, join, so we see it a little easier. And so this is the random name we are getting if we keep the probability of P. Now, this is not what we want to do. We now want to change this every time we are getting a new character. So if the first character is a K, then the next should be an H, and so on. Now, what we could do is we could look this up and basically say here random character, and this might work. Let's see what happens. So we get a different name, and actually we are getting, in this case it's always the same, we are getting a real good name already because we are not using the random W, but we are using the W counted. So maybe we want to see 10 names. Uppsala. And print this. So these names are not too bad, and let's re-enable this so we can have something reproducible for you. These names are not too bad. You see, some of them make sense, and we could now even go and say maybe somebody called their name their child Sionil or Vanian or Jester. But before we do this, let's see what would happen if we would use actual completely random names. So we still have the counted logics available to us later, and now we are initializing W with completely random names, and we are getting this. Now, what we've done here is interesting and works, but it's not something we can use to train because it's not differentiable. So here we are just picking out of this matrix and breaking things apart. And there's actually a way to do this in a differential manner. And the trick is the following. We have to use what is called one-hot encoding. For that, we need one-hot encoding from Torch, which is hidden in this functional library. And we usually import this as F. And we can do the following. We can now try this out and call one-hot and use a torch tensor of the random character. And now this will already work. Well, random character is that, oh, it is happening inside. It's happening inside the. Now what we really have to do is we have to actually tell one-hot encoding how many classes we have, and there's a parameter. It's got num classes, and here this should be the length of the alphabet. Now we get consistent output. Where this changes all the time. This is why this is complicated. So here a random character is 12. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so what you see is what it does is it takes, it creates a vector of 27 entries, and it sets the one that we provide here to be 1. So the interesting thing about this is that when we store this, and we call this X encoding because it's one-hot encoding, we can actually look at the output shape, and we will see that it has 27 entries, and it's essentially one row. Now let's remember what the shape of W was. It was a 27 by 27 matrix, and what you can do is you can now multiply these two matrices together, because we have some 1 by 27 times 1 by 27 by 27, so the result is 1 by 27. And so what it does is it actually gets just one row out of the W matrix. So this is exactly what we did here. We grabbed the row out. So instead of doing it this way, we can now go and compute the one-hot encoding of our random character. Then we compute the logits by doing xenc times W. Why are these logits? These are not probabilities yet. W is not probabilities. These are negative numbers, completely random numbers. This is typically what you would get out of a neural network. And then you run it through softmax. And we can do this by first exponentiating it. So then, and it's already recommending this here. And so the first thing that happens is all of the negative values become positive ones, and then I normalize by the total count of all of these numbers. So here I do this along all of the rows, not the columns, and keep them as true is so that I also get a 1 by 27 and not just 27 numbers. So if you leave the keep thems out, then this would become just a 27 value tensor, and then it might work here because of the casting, because counts is at 1 by 27, but better safe than sorry. So this is usually important to keep the dimensions the same. So now we have probabilities, and we can maybe we should visualize this real quick, all these little steps here. So the first thing is we want the logits and the counts. Let's get this all down here. So this is because xenc is not a float, but W is a float. So nice catch that we figured this out now already, and not just when we run the generate names. And by the way, we can also do this here, and we just get the exact same result because of the fact that we haven't changed anything, just use the different way of extracting these rows. So let's look at this again. So here I have to do also the float updated. It happens inside the thing. And so what we can do is we can look at the counts, which was something like this. And if we now do sum along 0 dimension, we're getting this. And if we do it along the first dimension, we get that. So the first time we didn't get what we want, we essentially summed up along each column, and that is just exactly the same as counts was before. So I'm summing up a first column, it's one entry. So what we want to do is we want to sum along the row, which we do like this. And now if you look at the shape of this, this is just a single value. But if I say keep dims equals true, then I'm getting a two-dimensional output, because the original input was also two-dimensional. And you see this doesn't change anything. Let's see what the item is looking like. I can get the item from here maybe. Does that work? So I'm getting the number. Either way, it's the same number, but my typecasting, my casting for the dimensions might get screwed up here when I have my counts, which has been a two-dimensional input. All right, so with this, we have a name generator that is actually differentiable, and we can now go on and implement the next step of our model. So if you want to train this, the next thing that we would need is a loss, and we want to minimize the loss in order to find the optimal W that would generate names as in the SSA database. So what is a good loss? In order to do that, we should first look at the way we can actually encode this problem as a prediction. And to do that, we grab a random name, which is not random because I bias it to using manual seed, and I grab it from the list random name equals names, and now I get my random function, and from 0 between the lengths of names, and it actually did it. Now I print the random name, and I already know the answer is Anais. And there you go. So this is what it selects when you set it to this. And this is an interesting name because it has two A's in it. So once an A is followed by an N, next an A is followed by an I. So this is already complicated because we will not get a completely straightforward training, and the loss can never be 0 because there's always some confusion left on what should happen after the A. So the next step we do with this random name is we tokenize it, and in order to do this we take all the characters in the random name, and we can then do a list comprehension and turn that into an integer. So we have something like this. And now we can think about the characters that should follow. So what should come after the 1, the 14? What should come after the 14, the 1? What should come after the 1 this time? The 9. And after that follows the 19, and then follows the empty character, which is 0. So how can we get this easier? Well, it's pretty simple. We can grab X just starting from 1. So it looks like this, and then we can make sure that the 0 is added at the end. So how do we do this? We add the 0 here at the end, and this should be something like this, and this is our target. See if that looks correct. All right, so there we go. So 1 is followed by 14, 14 is followed by 1, and so on. So if we want to have a good model, then the likelihood of 1 follows 14, 14 follows 1, 1 follows 9, and 19 follows 0 should be maximized. And so if you formulate this as a maximum likelihood, then the way that would look like is you would say the probability of this times the probability in times, means and this, and this. This probability should be maximized. And how is this maximized? It's maximized when the individual entries are maximized. So you can write this down in a formula like this. So we can use LaTeX in here, and so this would be the prot of let's say index I equals 1 to n probabilities, and that should be looks like that. This is the equation we have here. So this is what is known as the maximum likelihood. And what you can do is you can take the logarithm of this to turn this into a sum. And as you know, this might become a very, very, very small number if you have these low probabilities, and it's nothing like this to work with. So what you usually do is when you do a maximum likelihood estimation, you actually turn this into a sum by saying, let's enter this here. We can type this out here and say, let's say something like right arrow, and take the logarithm of this, which is ln up. And now this becomes the sum of I equals 1 to n of the log of pi. Let's see if this passes. That's what we want. So we are taking the product, which is the maximum likelihood, and we're turning it into a logarithm. Now there's one caveat here. As you know, we can get the torch log of a number, let's say 2 or 3, whatever. Oh, tensor, of course. So sorry, torch tensor. There you go. So I'm taking the logarithm of this, and this is close to 1. Now what happens when I enter 0, I get minus infinity, and for anything closer than 1, below 1, I get negative values. So now we are dealing with probabilities here, so all of these values will be negative by definition because they're all between 0 and 1. And so in order to minimize this, we actually want to minimize the negative log likelihood. And so that's what we're going to work with from now on. What we would have to do is we have to go and take our x and our y. Let me just print this here so we see them nicely next to each other. And what we have is our W matrix. And what we have to do is we have to go into the first row of this and say, okay, the first character is an A. And we have to look then, what is the next character? And this is the 14th entry, so it's a little complicated. How many are there here? 5, so 10. So this is the 14th entry. Actually, it's this one because we have to start with 0. So we are looking at this guy here. And we can actually do this and grab the first entry and the 14th. Oop. And we are getting the number that we just pointed out. So this would be the first probability. And so then in order to compute the negative log likelihood, we would take the logarithm of this and add, so it would be like this, torch log, and then we would add the torch.log w. What would be the next? It would be 14 and 1 and so on. So in this case, we are not doing this directly from the matrix W, but we are actually doing this from our logits. And as you remember, the logits were this. Logits was the encoding times our matrix, and what it did is it actually selects out the different the different rows that correspond to these characters in that order. So with this in mind, and maybe we should make sure that we have our encoding having flowed, otherwise we keep running into problems like this. And what we now can do is we have x and y. This is good. We should keep this. We should keep our equation because we will keep looking at that. And maybe we can delete all of these guys so get a little clarity. All right, so let's start. We have logits equals xang times w, which is the log counts. Now we compute the probability by doing the softmax operation. And I don't do this manually anymore because you know how it works, and this is easier and clearer. So now we have probabilities, and let's see how they look like. We have actually, in this case, we have only a single row because I didn't encode the entire name but only a single character. So what did we have? We have the random names Anais. So what we want to do is we want to take the entire name, and we do the one-hot encoding by taking our input tensor, which is the name Anais, and we have the num classes equals the length of the alphabet. And so then we want to do float to be sure we can multiply. Now, when we do the prop thing, we will actually get a list of 5 different probabilities like that. So you see we have 5 rows, 1, 2, 3, 4, 5, and this is the probability of the n-grams for A, this is the probability for the n-grams starting with N, this is the probabilities for the n-grams starting with A again, and here you can actually easily verify, yeah, this is exactly the same as we had here, because we are grabbing the same row. Alright, so now we have our probabilities, and we want to create a function that computes the negative log likelihood cost. And so now we can do the following trick. We can say that we want to get indices for each of these rows. So we just use the length of our input, and we have something like this. So the first number is in the 0th row, the second number is in the 1st row, second row, 3rd row, and then 4th row. And the other index is actually the value that we are having in y. So the 0th one we want to get 14, for the first one we want to get the first, for the second row here we want to get the 9th, and so on. So we can actually index our prop matrix like this. So this gives us the first entry, this gives us the second entry, and it will give us something like this. So we have 5 numbers. So the next step we want to do is we want to take the log of these numbers, because we want to get the log likelihood. We want to get the average of all of, actually let's do it step by step so we can see. So now it's the log, we want to get the mean, and then you remember all of these numbers are supposed to be, or expected to be, negative because they are between 0 and 1. So we want to get the negative log likelihood. So great, we get a loss, and for our current probabilities the loss is 3.2. So I think now we have all of our components. Just a small comment. The combination of negative loss likelihood, which is this kind of computation here, and doing the softmax afterwards is very common, and it's known as cross entropy. And so what we can do is we can compute the cross entropy using PyTorch's function, and we just say we have the logits, so we don't have the probabilities yet, so we didn't do the softmax step yet, and we are providing the answers that we want to get. And so you see here, this is coming out of y. So instead of looking this up individually using this function, I want to do all of this at once, and I will get the exact same number here. So the cross entropy loss is nothing else but the negative loss log likelihood after a softmax operation. So from now on we will use cross entropy, and you might want to read up on this again somewhere else, but I think this is also a very good example for you to see how we are getting the exact same result by running it directly using the logits as an input, and then, you know, providing the targets in the Y array. So with this we can do everything to do gradient descent, and as you know, this can be done by using the backward function. So I can say loss equals this. Now when you print the loss, you will see that it actually has a gradient attached to it, which goes all the way back to the weight matrix, which is the one that has a gradient true. So what I can do is I can call backward, and I will have after that I will have access to this information. So what we can now do is we can use PyTorch and implement an optimization using gradient descent, and we do this in this loop here. let's start something from scratch. Oh, that's a lot. Let's delete this whole thing here. And do this from scratch. As always, we do manual seed 42. We set random numbers. And we get 27 times 27 of them. And we want this to be something we can optimize against and track the gradient. We start with our random name Anais, and I like that because it has the two A's in it, I told you. And now what we can do is we can try to train this for 10 steps to start with, and we create our tokenized version from this for every C in the random name. And here there's a little thing that I want to do is I actually want to make sure that I take all of the characters, and this is because later I will not change this into a random name that comes from the list of names, and that is a has more dimensions than just this example here. And now I have to do my one hot encoding of my entire name. So I have to turn this into a torch tensor, otherwise it doesn't work. I have to tell it how many classes I have. This is the length of the alphabet. And then I want to make sure this is all a floating point number so I can multiply. So after I have my encoding, I want to create my targets, and these are the characters starting, just dropping the first one, but adding the space at the end. And so I know the answer here is 0, but now everybody sees, oh yeah, so we are adding the space at the end here. All right, so what's the forward pass? The first thing is we want to compute the logits by multiplying the encoding times W. So this takes out all the rows that correspond to the encoding of A, N, A, I, and S. So we get 1, 2, 3, 4, 5 rows. These are our logits. Then I want to do a softmax operation. And actually, I promised you to do cross entropy, but let's just stick to this and do it manually. We can change this later. And then we want to compute the loss by doing our, actually, no. I don't want to write this out again with all these A range things. What is our loss? Our loss is the cross entropy of the logits and the tensor of Y. That should do it for us. Now we can print this to see what's going on. We say this is a random name we're working on, and we give the actual loss. Then we set the gradient to 0 and compute loss backward. And finally, we update the data field of our probability matrix. Well, it should be minus equal 0.1 times W grad. So what happens here is, this is a little trick. When you do that, then Torch knows that you actually don't want to compute the gradients of this operation because you're actually accessing the data directly and overriding it. The alternative would be to write it out with, say, with Torch, no grad, and then do just W directly. But so this should do, and I think we should be able to run this and get something. And we see Anais gets trained, and it learns the bigram model just for this word. Let's see how far we can push this, and let's see what happens up to 100. And you see the loss keeps going down, so we have to train longer. Let's say we go to 1,000, and what happens is we are, well, 0.33, it still goes down. It's pretty slow training. So let's add something here. We only print this if the counter mod 10 equals 0. So if it's divisible by 10, we actually print, let's say, by 100. And then we go up to 5,000 here to see if we can get this to train. Now, would you expect this to go to 0? I don't. We are still only at, there's still some changes here. Let's go to 10,000 and see how this goes. And so you see it kind of like gets stuck at the 0.228. Now, this is expected. It can't go to 0 because we will always have confusion between, there's always a probability that an A is followed by an N or an I. So it can never perfectly, predict the name. So if you take a name like mine, which doesn't have that feature, there's no double alphabet entry here, then it will be getting probabilities to be 1 for all of these entries here, and the other probabilities will be 0. All right, so we can keep training this and bring the loss down to 0. Now, what happens though if we actually grab different names, and in this case we instead of fixing one, we take a random name from our list. And so this could be done by using, actually it already recommends this, it takes a random integer from 0 to whatever 100,000 to pick a random name. And you can now train, and you have seen it takes quite some time to get the loss down to 0 here. It takes 1,000, 2,000 iterations just to get here. So we wouldn't expect it now to learn much better, but we should see that the loss eventually goes down. So now we are 2.95, 2.38, 2.17. Maybe we should give it a little more so we can see if we enter new territory here. But we also wouldn't expect the loss to get to 0 ever, just because it doesn't get to 0 if you have conflicting information. Instead, the goal should be to get down to 0 and to as close as small as possible, so that we can then get the best possible estimate of what these probabilities are for our bigram model. So this is not a very efficient way to do things. We already know that we want to present this in batches, and now we can go and write code that will select 1,000 random names, presents them all at once, create a big matrix, and so on. So, but there are better ways to do this, and this is what we will do in the next video, where we will explain the PyTorch data loader.